Okay, great. Thanks very much for inviting me. So yeah, thanks Tamara and Chris for having me today, and thanks Phil for tuning in. So yeah, I'm going to be talking about some research that we've been doing in Southern Africa and Eastern Africa over the past 3 or 4 years, particularly looking at seismic hazard and also the tectonics of continental rifting in this region, which has some very interesting lithospheric properties, in particular, very thick lithosphere. Okay, so yeah, I should just mention this is not work that just I've done. It's really been a really great team effort, and part of that team is really been great to work with over the past 3 or 4 years. So I've listed everyone on here, but I want to particularly thank these 5 people in this photo here. So Ake and Juliet, who have kind of been the PIs on this Earth Sciences part of the project that I've been working on. And Jack, who was the postdoc who alongside me, so we were the 2 postdocs on this project that I'm going to be introducing. And yeah, we spent a lot of time in the field together working in this project. And also Patrick Chindandali and Hassan Mdala from the Geological Survey Department in Malawi. They've been really instrumental colleagues and have carried out a lot of the work that I'm going to present here. And really, this project would have been nothing without them. But also a range of other colleagues from both Malawi, but also from the UK, from engineering and earth sciences department in Bristol and further afield. Okay, so just to start off quite broadly, why are we interested in the seismic hazard in East Africa? And really, it's important to place this in the context of risk. So on the left-hand side here, I've got a plot of the magnitude 5.5 and greater earthquakes in Africa recorded since 1960. And you can see that broadly, the earthquakes are concentrated in this band, which corresponds with the East African Rift. But there isn't a huge amount of seismicity. If you compare it to example for just up in the northern end of this plot, you can see the Hellenic subduction zone. You can see there's much greater productivity up there in terms of earthquake numbers. So you might term that there's a moderate seismic hazard, although it is quite poorly constrained, and monitoring networks, especially in sort of southern and eastern Africa, are generally pretty poor. But if we look at the population density, and here I plotted actually the change in population density between 2000 and 2020, you can see that there's very rapid population growth within particularly the East African Rift, as well as the sort of Niger Delta area. And it's this high and growing population in the East African Rift that sort of increases the risk, alongside the very poor quality of buildings and high vulnerability to seismic hazard in this region. So this is an example of some collapsed buildings from a relatively moderate sequence of high magnitude 5 earthquakes that occurred in Malawi in 2009. And you can see, very high levels of destruction for what are very moderate earthquakes in many regions of the world. So really, we've been kind of approaching this high seismic risk in 2 projects that I'm going to briefly introduce over the next couple of slides. And the first of them was called PREPARE. So PREPARE, sort of counterintuitively, stands for Enhancing Preparedness for East African Countries Through Seismic Resilience Engineering. I would say that acronym was invented before I joined the project. But really, it was just a collaboration between earth sciences and engineering at the University of Bristol and the Universities of Cardiff. And then it had a really kind of key part of this project was training and education of our colleagues in Malawi. So within the Earth Science project, I'm going to talk through a lot of the results that we collected, but we were able to do sort of extensive field campaigns using GPS, remote sensing observations to answer some fundamental questions about how and why rifting is occurring within the sort of southern end of the East African Rift system. And the engineering parts of our project focused on in-country building assessments, developing new fragility functions for the buildings and houses in Malawi. And a lot of it was to do with testing materials, in particular the bricks. And then, as I said, a huge part of our project was training and education. So we held 2 workshops in Malawi to focus on seismic hazard and risk, and carried out a lot of training and collaboration with our Malawian colleagues, and they were also carried out some exchange visits. So we had 3 Malawian colleagues come to visit us for kind of extended periods in the UK. And the second project is kind of a follow-on project from our Prepare project. It was called Safer Prepared. It's primarily based at the University of Bristol, was to combine two projects. The first of which, Safer Schools, was started off in Nepal, addressing schools and making them resilient to seismic hazards in the aftermath of the 2015 Nepal earthquake, and then Prepare. And the aim of this project was to really increase seismic resilience within schools. And from an earth sciences and geology side of things, we aim to build on the work of Prepare to revise seismic hazard assessment through improved constraints on active faults. And all this was then to feed into an app which engineers in Malawi can use to actually make an assessment of the quality of the schools, and then you get a sort of picture of the resilience and risk that seismic hazards pose to schools in Malawi. And actually, this project really coincided with the pandemic, and so a lot of the work has been carried out by our Malawian colleagues, particularly Ignacio Ngoma, Hassan Amdala, Patrick Chinjandali, and Innocent Kafodja, and really is a testament to some of the training that we did during Prepare, that they were able to basically do a huge amount of the work on this project themselves. So I'm just going to now step back to kind of introduce the East African Rift, and particularly the western branch of the East African Rift, and some unusual kind of lithospheric properties that make this area interesting to study. So I'll start with this image, this figure from Tim Craig and James Jackson's paper from last year, which shows the seismicity on the left-hand side, and particularly the earthquake depths in this plot on the left here, and then estimates of crustal thickness from receiver functions on the right-hand side. And if we look at the western branch of the East African Rift, which runs kind of along here, so starting in northern Uganda, through Rwanda into Tanzania, Malawi, and then ending up here in Mozambique, and the depths of the earthquakes here are plotted on the bottom panel, we can see that seismicity extends all the way down to 40 kilometers depth, which approximately coincides with the depth of the crust as well. So these green dashes here are the crustal thickness estimates. As well as the thick seismogenic crust, we also have very, very thick lithosphere. So this is from an estimate of the lithospheric thickness from Priestley et al. And you can see here that the western branch of the East African Rift, just running through here, through Lakes Tanganyika and Lake Malawi, coincides with approximately 150 kilometer thick lithosphere. And it also kind of seems to coincide with the edge of these Archean cratons, which are plotted here in grey, and we'll come back to that later in this talk. So as well as this very thick crust, thick seismogenic thickness, and thick lithosphere, we also have very, very long faults. So most of the extension within this kind of strong, thick amagmatic lithosphere is thought to be accommodated, or was thought to be accommodated, on very, very long border faults at the edge of the rift. So one of the most famous, especially among the COMET community, is the 100-kilometer long Belila Mataka fault that James Jackson and Tom Blenkinsop wrote about in 1997. They mapped out the fault from Landsat data. They actually, as far as I'm aware, flew an aeroplane along the faults and discovered a really clear sort of 10 to 15 meter high fault scarp that was exposed right the way along this sort of 100-kilometer long fault. And they hypothesized that this may have been caused by a single magnitude 8 earthquake. So this kind of thick, strong, cold lithosphere that we have in Southern Africa allows us to investigate this broader question about the plate force paradox. And the plate force paradox is that the tectonic forces driving continental extension are not sufficient to rupture thick, cold continental lithosphere. So although from kind of global geodynamic models, we know quite well the sources of buoyancy within the mantle, because individual measurements of the strength or rheology of rocks as a function of temperature and pressure is poorly known. There are many parts of this kind of diagram that we struggle to understand and to model. And in particular, the intralithospheric heterogeneity. If we don't know the strength of the lithosphere particularly well, we struggle to address the forces that drive continental extension within the lithosphere itself. So just to summarize what I've just said there, so we know that the western branch of the East African Rift is hosted in thick, 150-kilometer thick, old and cold lithosphere, with seismicity extending throughout the 40-kilometer thick crust. The rifting in this region is largely amagmatic, with deformation thought to be accommodated on long border faults at the edges of the rift. And our current attempts to understand the rheology are incompatible with recent research. So this comes from a paper by Ake Fagarang in 2013, where he used the heat flow constraints within the Malawi Rift to try and understand the strength of the lithosphere, in particular why we might get earthquakes so deep. And it's actually quite difficult to reconcile this deep faulting with the composition of the crust. So if you were to model it with a felsic lower crust, it's incompatible with the deep earthquakes. If you introduce a mafic lower crust, it's incompatible with crustal observations of seismic observations of crustal compositions. So that introduces sort of the one broad question I want to address in this talk, and that is how is strength distributed within the lithosphere? But also, as well as that, there's plenty of crossover between this kind of broad scientific question and how to apply that to seismic hazard research. So in particular, if we can answer how deformation is distributed along the surface of the Earth and across individual faults, we can address this broader question, as well as wanting to understand how faults reactivate along pre-existing structures at the edges of the cratons. And finally, we really want to address this question that Jackson and Blenkinsop hypothesizes, whether these 100-kilometer long faults really host, potentially magnitude 8 earthquakes or not. So to answer these questions, we basically conducted a series of kind of experiments and observations in southern Malawi over the past 3 or 4 years. So this is a region just at the southern end of Lake Malawi, where active faults are kind of subaerially exposed at the surface. And this is just a small map of that area that we've been studying. And this was the kind of picture that we were faced with as we started this project. So we knew about this one fault. This is the Bulila-Matakataka fault. And we had 2 GPS stations that had been kind of previously installed that were measuring deformation in the region. So to answer these questions, I'm going to take a kind of 3-pronged approach. So starting off, I'm going to look at continental scale deformation and plate models using GPS. I'm going to kind of zoom in a bit, looking at deformation within individual rift basins using some high resolution topography. And then before looking at a sort of a finer scale deformation within individual fault damage zones. And so this kind of multidisciplinary approach allows me to reveal some important aspects of the strength of the lithosphere and the rheology, and also allows me to inform some seismic hazard assessment, which I'll finish on in this talk. Okay, so starting off at kind of African scale. So this is a picture on the right here. I've got the African continent, the topography, and the earthquakes greater than magnitude 5 in the ISC GEM catalogue. The focal mechanisms are from Tim Craig's compilation of African focal mechanisms. And plotted over the top in the red lines is the current plate boundary situation up until about a year or 2 ago. So most of Africa is thought to be part of this Nubian plate, and the East African Rift essentially accommodates extension between Nubia and Somalia with a couple of smaller microplates. This is the Victoria microplate, and this is the Rovuma microplate. But one of the problems with this kind of plate model is that there's a huge amount of deformation occurring away from the main kind of Nubian Rovuma Victoria plate boundary, in particular in this region to the west of Malawi and Tanzania. You can see there's lots of relatively large magnitude earthquakes that aren't being accommodated at the plate boundary. So we wanted to kind of explore how rigid Nubia is as a plate and whether it is operating as a single plate or whether it could be described better by a different plate configuration. So what we did was to establish some new GPS sites in southern Malawi. So in general, this region of southern and eastern Africa has very, very few GPS sites, and there's only, I think, about 5 or 6 between kind of Tanzania and southern Zimbabwe of permanent GPS sites. So we established campaign sites in southern Malawi in 2016, courtesy of some COMET funding, and then the Prepare project has funded approximately yearly campaigns since then. And so what we want to do is to explore whether this Nubian plate is operating as a single plate or whether it's better modeled as a separate plate. And this was really influenced by some research or a paper that was came out in 2020 by Mike Daly, who suggested that there might be a potential plate boundary that follows the southwestern branch of the East African Rift. So first of all, we took the GPS observations from Nubia and the what we might call a three-plate model. So where Southern Africa is part of Nubia, and we have Rovuma and Victoria. And in order to test this, we're going to carry out a statistical test. So we add up the chi-squared from this original plate configuration, and we get a value of 115.6. And if we introduce this new plate boundary and this new plate, which Daly hypothesized existed, and model the plate motion there, we get a reduced chi-squared of 85.9. So using a nested F test, we clarify that reduction in the chi-squared value is statistically significant at a 99% confidence interval. In other words, we can be confident that this sand plate is moving independently from Nubia, and this plate boundary, which runs along the southwestern branch of the East African Rift through Zambia into Botswana and then eventually Namibia, is an active plate boundary. So this is quite satisfying from a number of reasons. It satisfies the benefit to the GPS data, but it also accounts for active faulting along the southwestern branch of the East African Rift. So Mike Daly, in his paper, spotted some signs of active faulting, and then I had a master's student last year, Tess Turner, look for signs of sort of late quaternary faulting within the northern Zambian Luangwa Rift. And she found really conclusive evidence that there's been relatively recent earthquake rupture on some of these faults. So this particularly clear fault scarp that you can see in this slope map from the Luangwa Rift coincides really nicely with two earthquakes that occurred, one in 1919 and one in 1940. You can see these locations for the 1919 event slightly differ depending on whether you use the USGS or ISC catalogue. But they're broadly in the region of this very, very clear and conspicuous fault scarp. So we think that may well have been reactivated during those events. The other thing to note about this new plate boundary that we've introduced, is it bears a close resemblance to the edges of the Archean cratons in southern Africa, and particularly the northern edge of the Zambezi craton and the southern edge of the Bangweulu block, the BB, which we've labelled here. And these cratons, we know they're comparatively rigid compared to the surrounding metamorphic belts. And so we suggest these compositional differences between the cratons and the metamorphic belts is driving strain localizations at the edge of the cratons. And the other thing that we speculate in this paper, and you can read more, it came out last year in JRL, is that there potentially might be more of these smaller microplates if we start to include this kind of deformation that occurs at the northern edge of the Bangweulu block and the southern edge of the Congo craton. But currently, we just don't have sufficient GPS data in order to constrain that in this region. So next, I'm going to zoom back into southern Malawi and focus a bit more on the rifting there. So as I mentioned before, we knew prior to our project starting that there was probably one active fault, the Balila Mataka fault. This is a greater than 100 kilometer long normal fault with a 15-meter high scarp, possibly the host of magnitude 8 earthquakes. There was two GPS stations in the region recording an extension rate of approximately 2.2 millimeters per year, but no continuously recording seismic stations. And the only significant earthquake to have occurred in this region was a magnitude 6.1 earthquake, which occurred at 32 kilometers depth. And the reason we're really interested in this event is because, one, it's particularly deep, but also the World Bank recently calculated that if this event was to occur today, following the rapid population growth that I outlined in the first slide, it would cause over £85 million loss and up to 650 deaths. And to put that into context, that's nearly 1% of Malawi's GDP. So that's a huge hit to the Malawian economy. So this is kind of an updated situation following our project. So we now have mapped 14 active faults where we've observed recent activity, so late quaternary activity, and there's a bunch of papers that we've published on that. And there's evidence for multiple magnitude 7 earthquakes on these faults, which are typically between 50 and 100 kilometers long. We have 14 campaign GPS stations that we've occupied approximately yearly since 2016. And that includes during the pandemic. So fortunately, our colleagues in the Geological Survey Department in Malawi have been able to carry on occupying them over the pandemic over the last 2 years. And all of these faults, together with some faults in Lake Malawi, have been incorporated into an active fault database that follows guidelines from the Global Earthquake Model. And I'll talk more about that later in the talk. Okay, so how do we go about mapping the active faults? So we're going to just go back one slide. So I'm just going to zoom in on one particular graben. This is the Zomba graben in southern Malawi. And this is where I kind of focused a lot of our research at the start of this project. So we went about using a TandemX 12.5 meter digital elevation model. So we found this was a kind of good compromise between the sort of really high resolution products you get from stereo satellite pairs with the kind of spatial coverage that we needed to cover large areas of this rift system. So we used this data to map the faults, and the key indicators that we were using in this TandemX data was offset of late quaternary sediments, in particular these really kind of linear high slope features that you can see through this slope map here that seem to indicate active fault scarps. And these generally aligned with increases in river channel steepness that we mapped out from interpreting the river channels as they cross the faults. So as well as using this high resolution digital elevation models, we verified the vast majority of what we thought were active faults during field work by going into the field, looking for evidence of these scarps, looking for damage within the footwall fault zones, and also potentially looking for indicators such as slicken sides on the fault planes as well. So these are some images of what the faults look like in this kind of 50-kilometer wide Zomba graben that we map using TandemX data. So this is one particular fault. This is the Zomba fault itself. So this late quaternary fault has offset these alluvial fan sediments coming out of this river channel by up to about 30 meters in this case. So we have collected now some cosmogenic exposure dates from the top of this alluvial fan surface. We're still waiting on the results from them. This is another particular fault. This is probably my favorite fault, the Mulungusi fault. So this fault cross-cuts the Shire River, which is the main river which drains Lake Malawi. And it's really clearly exposed in the landscape. It seems to offset what seemed to be previous lake sediments in the sort of center of this graben. You can really clearly see the fault on this drone image, but it's also extremely clear in the field. So has this 6 meter high scarp offsetting these lake sediments, but also really clear to see in the DEM as well. So this is just a transect across the scarp, and we see here approximately 7 meter high scarp in this case. So again, we mapped more of these faults. So this is the Chingale step fault. Again, a sort of 15 meter high fault scarp, similar to the scarp that Jackson and Blenkinsop noticed on the Blina Matakataka fault. And when we actually mapped this in the TandemX data, what we found along large portions of the fault, that there's actually kind of two generations of fault scarps. So a lower fault scarp, approximately sort of 10 meters high, and then a multi-scarp, so a cumulative scarp, probably representing more than one earthquake, approximately 20 meters high. So what we did was to map out the scarp heights systematically across all of these 5 faults. So taking transects systematically every 100 meters, stacking those transects, measuring the scarp height. And we found that the scarp height varied between 5 and 30 meters. So the 5 meters tend to be on these smaller scarps on the western side of the graben, but on the eastern side, we measured up to 30 meter high fault scarps that I showed a few slides ago. So what I then did was to take those measurements of scarp height that I showed on the previous slide and calculate the strain using a Kostrov summation of surface deformation. And so that's shown in the bottom right-hand figure here. So various assumptions were made there because we lacked a lot of kinematic information. So we assumed these were normal faults, but we didn't find any evidence to indicate any strike slip or even any sort of transtensional deformation. So we're pretty confident these are normal faults. And the one slick side that we did find was indicating essentially pure normal motion. So what we found was that, to our slight surprise, that actually a higher percentage of the strain occurred across the intrabasinal faults than the border faults. So it was higher, but within error. So we like to think approximately 55% of the strain occurred across the intrabasinal faults and 45% across the border faults. So contrary to that expectation that I showed earlier in this talk, that most of the deformation in this region should be accommodated on the border faults, it seems that actually there's a higher percentage of strain within the interior of these basins than anyone had previously realized. And what's quite nice, this paper was published in Tectonics in 2021, and Donna Shillington, who'd been researching kind of the northern basin of Lake Malawi, came to a pretty similar conclusion in the same edition. So it's worth having a look at that paper as well. So why is the deformation more distributed within the Zondergraben than we previously thought? So we came up with kind of two broad scale reasons that we're going to discuss the reasons for them in this slide. So the first is that the current distribution of strain may represent a period of time prior to localization of strain across the rift border faults. Now, we don't think that's the case, because if we look at the topography of this graben, we can see that especially on the eastern edge, we have this really clearly defined border fault with a large footwall escarpment, nearly a kilometre of relief in the footwall. So we think that there must have been a period of localization on the border fault, but now we just have a period where there's increasing strain within the intra-rift region. So we have this intra-rift faulting continuing after a period of strain localization across the rift border. So why might that be the case? So one reason could be that the border faults have kind of locked up, they've ceased activity due to flexure. But this kind of mechanism requires very, very large offsets, so many kilometers that are just not present within the Zondergraben. So the sedimentary cover in this region is probably less than about 200 meters, very, very thin, and we only have about a kilometer of relief on this border fault. So not enough deformation to induce the kind of to cause the border fault to lock up. So one reason could be fluids. So magmatic fluids and volatiles facilitate extensions at much lower stresses than available tectonic forces. But there's really no evidence for active magmatism beneath southern Malawi. We're about 800 kilometers from the nearest volcano. But there could be some decompression melting or low crustal magmatic intrusion that we aren't able to image, or hasn't been imaged using any seismic methods. So we can't rule that second one out. But our kind of favored interpretation is lateral heterogeneity within the lower crust. So we know this is a very old kind of Proterozoic lithosphere. It's been through many phases of previous deformation. So it's likely that there's a sort of strong competency contrast within the lower crust. And this would enable relatively distributed deformation within a narrow rift in otherwise very strong lithosphere. And crucially, it does not require pre-existing frictional weaknesses in the upper crust. So there's been some experiments on the shallow rocks from Malawi, and there's no evidence of any sort of pre-existing frictional weaknesses in that region. So we don't have to invoke that mechanism if we think there's lateral heterogeneity in the lower crust. Okay, so secondly, just moving on to kind of assessing fault segmentation in this region, and this is particularly important for our kind of seismic hazard constraints. So to look at that, we studied a fault right at the southern end of the Malawi Rift, the Tiolo fault. And in particular, because this is really well exposed, this fault, but it had a really interesting structure within its footwall, which allowed us to investigate, and particularly the effect of near surface heterogeneities and structural orientation on the activity of these faults. So this figure in the top left-hand corner is a figure from Michael Hodge along the Belina Matakataka fault. And what he found was that the Belina Matakataka fault was indeed segmented, But these segments didn't really correspond to any change in the shallow structure of the fault. So you can see here that at times the fault cross-cuts the foliation, at times the fault follows the foliation, and there doesn't seem to be any reason that these segment boundaries kind of follow those changes in polarity. So we looked at the Tiolo fault, where it has a kind of two really clear pre-existing structures within the footwall. So these black lines, that's some Karoo-aged dikes. So these are northeast southwest trending, and you can see this is a rose diagram of the orientation of those dikes on the right-hand side here. The yellow dip symbols here is the orientation of the foliation within the footwall. So this is a sort of Proterozoic foliation, and that's shown in the yellow rose diagram here. So as well as the pre-existing structure within the footwall, we had this really clearly defined active fault, which is shown by the red line, the red rose diagram. And within that fault, we notice these really clear sort of 90-degree turns within the fault. So this is the most prominent one here, but there's also some smaller ones, approximately sort of 50 to 100 meters long, further along the fault. And these are shown in the blue rose diagram. So the first thing to notice is that the fault seems to really clearly follow the orientation of the foliation, whereas these kind of what we term the linking segments, or these 90-degree segments, really clearly seem to follow the orientation of the Karoo-aged dikes. And you can see that in this next slide. So the strike of this Tiolo fault here, plotted in red here, really clearly follows, and in these stereonets here, clearly follows the orientation of the metamorphic foliation, whereas these 90-degree segments coincide with the orientation of the pre-existing dikes. So this suggests quite strongly that the segmentation on this fault is controlled by some pre-existing fabrics. However, I should also just add that this fault really, again, clearly displayed kind of late quaternary activity. We saw a sort of 20 or up to 20 to 30 meter high fault scarp consistently along this fault. However, when we looked at the late quaternary scarp, and we systematically measured it along the fault, we saw that there was these kind of three clearly defined segments, or defined by these minima in the scarp height at the sort of segment boundaries. But the changes in the scarp height, and particularly these segment boundaries, bear absolutely no resemblance to the segment boundaries we identified just based on the kind of changes in the strike or orientation of the fault at the surface. And you can see, I just highlight that even more. So you can see that these changes in strike on the second plot here don't bear any resemblance to where we see the throw minima. So what we think is occurring along this fault is that these kind of what we think are low cohesion structures, shallow structures, the foliation and the edges of these dikes are unlikely to continue to depth. And in addition, the foliation itself does not contain any frictionally weak materials. So what we think is occurring is that these shallow structures are controlling the orientation of this fault, but not actually the segmentation of it, which is probably controlled by something deeper, the deeper structure. So as well as looking at the fault scarps along that fault, we also looked at deformation within the damage zone of that fault. So here's a nice cross section exposed in a quarry that happily was kind of oriented perpendicular to the scarp, which has been a bit of kind of quarried away here. And we looked at that both kind of for macro scale evidence of fault damage, but also in thin section. So this is what the fault looked like, the fault damage zone looked like at a kind of macro scale. So over the course of about 50 meters, we see a change from very, very competent basement rock, undamaged. You can see this pegmatite vein that I've picked out here is not being offset. As you go kind of closer to the fault, we start seeing some deformation across an exhumed shear zone with some increased levels of fracturing. And then getting about 20 meters away from the base of the fault itself, we saw quite heavy fracturing, offset pegmatites, associated with much higher levels of deformation within the damage zone. And this is replicated again at a micro scale. So these are photomicrographs of fractured quartz and feldspar grains within the fault damage zone. And we've just traced over the fractures there, and you can see this increasing in fault damage as we get closer to the fault. But the really important thing to note is that this is very, very restricted to the nearest 50 meters of nearer the fault. So this is approximately an 80 kilometer long fault. And generally with kind of fault length, damage zone thickness scaling relationships, this should be a much, much wider fault damage zone, up to a kilometer in some examples. So we actually have a very, very narrow fault damage zone along this fault. So this is our kind of interpretation of that damage zone. So what we think is happening is that the narrow fault damage zone is associated with localized strain along reactivated shallow low cohesion structures. But these low cohesion structures are unlikely to be the result of the segmentation of the fault. So that's likely to respond to much deeper structure. And we possibly associate that with the fault being at the edge of this Unango Proterozoic terrain boundary. But what we hypothesize is that if this kind of narrow localized strain continues to depth, an increase in strain rate within a narrow shear zone would then increase the brittle ductile transition depth, so potentially explaining those deeper earthquakes that we see in this region of the Rift, and the thick seismicity occurring right to the Moho. Okay, so that's kind of moving now back to the more kind of seismic hazard and applied parts of this talk. So I've detailed there quite how we kind of gain these insights into the rifting in this thick lithosphere. But I want to talk about now how we've used that information to actually map seismic hazard. So the first thing that we really did was actually produce this active fault database, the Malawi active fault database. Now, this isn't simply just a map of the active faults. It really contains detailed information about the sub-area exposure, the dip direction, and all the parameters of an active fault that you would need to then incorporate that fault into probabilistic seismic hazard assessment. So on the left-hand side here was a kind of fault map that was produced just before we started this project. So you can see that it's only really mapped out the border faults in the Malawi Rift, which was what people previously thought were the kind of main active faults in the region. So what we did was to combine our observations from high-resolution topography and fieldwork, where we mapped the subaerially exposed fault scarps. We used some aeromagnetic data to map the blind faults, and also the seismic reflection data that had been collected within Lake Malawi, particularly during a recent project led by Donna Shillington and Chris Schultz in the US. And to produce this active fault database. You can see the vast improvement in the number and resolution of the active faults that we've mapped in Malawi. But a key part of this active fault database is that it's been really developed in collaboration with the Geological Survey Department in Malawi. So as part of our workshops, this was a co-produced fault map. Here's some of our Malawian colleagues discussing the active fault map during a workshop in 2019. And here's Hassan Mdala, who's really led the development from the Malawian side. And he also spent a month in Cardiff working with Jack Williams and Ake to really produce this active fault database. So the key thing to construct in constructing this database is followed the global earthquake model template for producing an active fault database. So these are just a snapshot of some of the attributes that we include within the active fault database, so things like slip type, geomorphic expression, dip direction, and as well as that, we produce it in a wide range of data formats so that as many different people can use it as possible. And a really kind of integral part of that is making it freely available and open source. So we have a release on Zenodo, but actually what we do, we maintain this GitHub database so that anyone can access it anytime, but also anyone can suggest updates to it. And in the long run, what we're really looking to do is to hand that over to our Malawian colleagues, so they will take charge of that in the future. So they'll be responsible for their own active fault database, which is correct. So we're also beginning to kind of expand this work to other rift basins where we've been working with local geological surveys in East Africa. So this Malawi active fault database has now been included within the GEM global active fault databases. Here's the GitHub update on Richard Staren's global active fault database. But we had a master's student in Bristol last year, and she worked on constructing an active fault database for the Luanga Rift. And we're currently working alongside that along with colleagues at university in Zambia, in Lusaka, and also working with Ugandan colleagues at the Ugandan Geological Survey Department to construct an active fault database within there as well. So in order to go from this active fault database to seismic hazard, we use a lot of the parameters that I established in the early part of this talk. So things like assessing fault segmentation. We use that to calculate earthquake magnitudes, using the new constraints on rift extension rate that my new plate model gave rise to, and also using trying to understand the percentage of extension accommodated across these rift basins by individual faults. And from that, we then produce a seismic source database. Again, we have uploaded that onto Zenodo and GitHub, and that paper is currently in review. And this is just one example. This is the seismic source database, but we also have a segment database and a multi-fault database. And key to going through these steps is to apply uncertainty through a logic tree approach. And that involves weighting the different seismic source scenarios. So whether how to weight the sort of segment, whole fault or multi-fault ruptures. We then create an stochastic event catalog, incorporate background seismicity rates, and then use a range of different ground motion models. And this is one of the first examples now of our seismic hazard assessment that we've produced for the whole of Malawi, incorporating both onshore and offshore faulting. So this is just one example of 2% probability of exceedance in 50 years. And this represents a huge advance from previous studies where most of the seismic hazard was presumed to be either kind of uniform across the whole country or concentrated around individual border faults. Okay, so just to summarize, so in this talk, I've shown how we use high-resolution topography, field observations, and GPS data to show that the sand plate in southern Africa is statistically distinct from the Nubian plate, and the southwestern branch of the East African Rift system forms a boundary between Nubia and Sam. And the implication for the kind of understanding of the rheology of the lithosphere is that strain in southern Africa is concentrated in these Proterozoic metamorphic belts between the Archean cratons. When we looked at kind of individual rift basins, we found that up to 30-meter high active fault scarps, and that strain within the interior of these rifts is much, much higher than previous models suggested. And from that, we suggest there must be some lateral heterogeneity within the lower crust, which is enabling distributed strain within otherwise quite strong lithosphere. And the near-surface pre-existing structures seem to control fault orientation, but not necessarily segmentation. And that fault zones in southern Malawi are very narrow compared to, or given the amount of displacement the faults have accrued. And we suggest that these narrow fault zones, if they continue to depth, might promote higher strain rates within shear zones, which would enable deeper brittle faulting. So yeah, I think that's everything. Thanks very much for listening, and yeah, I'll take any questions.
Well done. That was wonderful. I really enjoyed that talk. Thanks, Luke. We already have 2 questions, but do feel free to put any questions in the chat if you have them as they come up. And if we have time, I have a few as well. But first off, Jenna Chafer has asked, with the KC craton in the south, do you have any comment as to why we see relatively shallow faulting within the craton, considering you mentioned that we see faulting along the perimeter of rigid cratons?
Okay, yeah, so I mean,
so this is in the Q&A box.
Yeah, just looking at it. Yeah, so I think some of that faulting might be related to some mining, so it might be mining-related seismicity. I think that's potentially what she's referring to. I'm not totally sure, but there is a kind of contrast in Malawi itself between areas where we see this really, really deep faulting. So the earthquake in 1989 was one example of that, which occurred down to around about 35 kilometers depth. And then in northern Malawi, the 2009 earthquake sequence there occurred on really, really shallow faults down to about 10 kilometers. So we do see this kind of contrast in faulting between the really shallow and deep crust. So I think in 2009, Juliet had a paper with a number of COMET colleagues where they suggested that the shallow faulting might have been associated with kind of breakup of these hanging wall faults, possibly associated with flexure or some just shallow faults that kind of have started to appear as a result of the breaking up of these hanging wall, these large kind of border faults. But yeah, we certainly do see the shallow faulting and the deep faulting. I'm not quite sure how that relates to the craton, but generally most of the deformation occurs away from the craton edges, with some exceptions in southern Tanzania, northern Tanzania. But yeah, generally it's away from the cratons itself. Hope that answers your question, Jenna.
If you have any follow-ups, Jenna, feel free to put them in the chat. Oh, she's saying thank you. So I think that's answered the question. So Ed Rhodes has asked, what is the risk of tsunami generation at Lake Malawi from lake bottom normal fault movement?
Yeah, I wouldn't rule out that being a hazard. I think, yeah, I mean, we certainly see displacement across very recent displacement across the lake bottom fault. So Donna Shillington and colleagues in the US have been working on that. They have this really clear, prominent 75,000-year-old reflector in the lake basin data, which they've been able to map out kind of where the most recent faulting has been in the lake, and they see displacement a lot across the lake, the base of the lake. But what I've always been a bit more concerned about, and actually when I went into the field with Grace Campbell from Arup a few years ago, she was really concerned about this as well, is the possibility of kind of seizures induced from landslides, because these tend to be really steep slopes surrounding the lake, in particular in the footwalls of these normal faults. So any landslides that might come off them could induce quite large kind of waves as a result of that. So I think yeah, we couldn't rule out tsunamis, but also these kind of landslide induced seizures are definitely another hazard that we should be aware of, I think.
I have a quick follow-up to that. Are you aware of any studies looking at sort of paleo tsunami or seizure deposits at the edges? No,
I don't think anyone's ever looked at it. Yeah.
Cool. So Catherine Marai, apologies for pronouncing your surname like that, asks, why is the western branch amagmatic?
Yeah, I think that's a very good question. One I'm not necessarily in a position to answer, but so I think there's a number of theories. So one theory is that it's not as evolved as the eastern branch. So in the eastern branch, there's much higher, much more total extension, so much more thinning of the lithosphere, allowing the kind of astenisite to rise up and melt the crust, and obviously so that's one idea. I think the other kind of potential idea is that the composition of the lithosphere in the western branch is different, so less easy to melt. I think that that's my main understanding about. Yeah, I'm not an expert on melt and volcanoes and things like that. So yeah, I would. I'm sure there's people who might be able to answer that much better than me.
Brilliant. We have another question here. So Stefan Trovac, again, apologies for my pronunciation, says, thank you for your presentation. I've enjoyed it. I was quite surprised with the strain accommodation in the center of the rift rather than in border faults, especially in this quite young stage of rifting. Did you observe an increase of seismic activity in past years? And last thoughts, what are your thoughts on future development of EARS? Yeah,
so I think, Stefan, I agree with you. We were surprised by the fact that there was more strain, or sort of equal amounts of strain within the interior of the rift and at the edges. And I think that's one of the big things to come out of this research. But also, what was, as I mentioned in the talk, what was nice is that Donna Shillington had a paper which came out in the same edition of Tectonics, where they also found the same kind of result in northern Malawi. So I think we're still at although I suggest this kind of lateral heterogeneity could explain that, I think we still need kind of better seismic observations of the kind of the structure of the crust in this region to try and explain that, because it is difficult to explain where you have this really thick, strong crust as how you get this distributed deformation. And certainly from looking at so we don't necessarily see an increase in seismic activity within the past years. So most of the seismic activity that we see in southern Malawi to today is related to aftershocks from the 1989 event. So Vicky Stevens in UCT had a paper which came out last year where they deployed some seismometers in a kind of array formation at the southern end of Lake Malawi, and we found there was quite a lot of seismicity still occurring up to magnitude 4. It wasn't being picked up on these global networks, and essentially that was related to the 1989 or aftershocks. We think that was related to aftershocks of the 1989 event. What are your thoughts on the future development of the EARS? Well, it's a good question. I think, it's obviously going to continue going. But what I think the key aspect of my research has revealed is that we shouldn't just be focusing on the kind of western and eastern branches. This southwestern branch is really important to look into as well. And it kind of completes the picture of Africa. Everyone knows about the Okavango Delta and the Okavango Rift, but it puts it in the same kind of broader context of this longer rift system that extends from Ethiopia right into southern Africa. So I think, in terms of research, that's where I'd like to see a bit more research in the future, because I think it's probably an underappreciated hazard in that region.
Cool, thank you. So Saturday, Usufo has asked, South Africa is part of Nubia Plate, but from one of the maps shown, does it mean the sand plate is a new plate? And if yes, do you have any articles that you can refer them to?
Yeah, so I think, hopefully I showed in this talk that our GPS data can show that the Southern Africa and South Africa in particular is moving independently from the northern part of Nubia. So yeah, we have modeled it as a new sand plate. And yeah, I suggest there's a paper in Geophysical Research Letters that came out last year that you can read to find more information about that.
Cool. I have 2 questions if I can sneak them in. If you have any other questions in the audience, please do put them in, but while we've got a bit of a break. My first question was, what is the seismometer network like there? You sort of mentioned that there was a deployment that picked up magnitude 4s that weren't on the sort of global networks. Are there permanent seismometer stations? Are there plans to deploy any?
So there are very, very few, especially in Malawi, but generally in kind of southwestern Africa. So in Malawi itself, as far as I'm aware, that there was one permanent station associated with Africa Array, but then a part broke and they haven't been able to get it back running again. Vicky Stevens and Al Sloan from UCT deployed this network, and they ran it for about 4 months, and discovered a huge amount of seismicity that no one had picked up before. So I think if there has been a large effort in Africa, particularly from Andy Nyblade, to try and get a much better network of seismometers across the region through Africa Array, but it doesn't have anywhere near the amount of coverage that many other areas around the world do, and I'm sure there's a lot of events that we are missing as a result of that.
Yeah, right. I wonder, this is totally an aside, but are you aware of any institutes or anything trying to put in money to improve local capabilities?
Not as far as I'm aware, no. I mean, I'm sure that there's been a lot of, there's a lot of European and American kind of isolated projects, but there's no long-standing infrastructure, which is what it needs. So there is a few exceptions to that, and there's a few countries who are really making efforts. So I think Uganda is one. They have when we went there, they had a much better seismic infrastructure and a couple of really good people running that. But often it takes, it's just the one person who's kind of running their country's network, and if they go or leave for a higher job, which is quite common, then that network kind of loses energy and it doesn't carry on, which is a shame.
Yeah, for sure. And I imagine I don't run a seismometer network, but I imagine it's quite expensive to keep them running.
Yeah, and you know, the other thing to think about is that seismic hazard is not high on a lot of these countries' kind of priority list, so they're much more concerned about floods, windstorm, that sort of thing. So we have to put that in context as well. For sure.
I have one more question, if I'm allowed it. I know we're at time, but I wanted to ask the interior deformation, the faults in the interior of the rift zone. There didn't seem to be much topography associated with them. So do you think that these are sort of one-off events that move around within the rift, or are they just very young faults?
Yeah, that's a good question. So I think I don't think they're one-off events, because I think on one of the interior faults we found evidence for at least 2 events. So they're definitely not one-off, but I mean 2 events is not many, is it? So I agree. They haven't got a huge amount of topography in the footwall, and some of them have kind of lake bottom sediments in the footwall as well. So they may well be slightly buried. So that one I showed, which is kind of in the right in the middle of the rift, which is sort of 5-6 meters high, that definitely is partially buried. The sort of cumulative deformation is partially buried by some paleo lake sediments, I think. So I think there probably is more than one earthquake, but I also think that they have become active relatively recently as well. So, but within the lake itself, with the sort of segment project and Donna Shillington's work, they show that these faults are quite long-lived up there. So it might just be that the sort of strain or extension rate in southern Malawi is much lower than in northern Malawi, so that they haven't been as active as long or aren't needed so often to accommodate deformation.
Yeah, cool. Thank you. And I think that's all the questions, and we are on 5 o'clock. So in order to keep to time, I think I'll call it there. But thank you so much, Luke. This has been a wonderful talk. I've learnt heaps, and I'm sure our audience has thoroughly enjoyed it as well.
Thanks very much for having me. I've enjoyed it a lot.